Thank you all so much for joining us. My name is Jamika Marshall, and I am pleased to serve as the coordinator for the Shadow the Scientist initiative. In this session, we have the privilege of shadowing members of the Gemini North observing team. And that tonight is Charlie, Denise, and Layla. They will be making observations remotely from the control room in the Hilo Base Facility. Now, we will also be joined by special guests from the Gemini North staff who will showcase the next exciting instrument that will be available to the Gemini North community. That is the second generation of the immersion grading infrared spectrograph. Let's head over to our guides on this cosmic journey, Brian Lameau and Emily Peavy, so they can introduce themselves and get us started. Brian, Emily, how's it going over there?
Aloha, Jamika. It's going well. We are troubleshooting our connection into it, and we're going to have the connection to our control room in just a moment. In the meantime, aloha, everybody. My name is Emily Peavy, and I'm the Senior Education and Engagement Assistant here at the International Gemini Observatory. So a lot of my work is I'm a scientist focusing on how to communicate science to other people and think about how we can bring all of these amazing things that we're learning about the universe down to Earth and make it understandable. And Brian, do you want to introduce yourself?
Yeah, sure. I'm just going to switch computers real quick. So
there you go. Now you're
awesome.
Now you're able to talk to us, Brian.
Okay.
Yes. Okay.
Okay. Aloha, everybody. My name is Brian Lameau. I'm a staff scientist here at Gemini North. I am one of the many scientists here who help with the telescope and help the telescope run and use the telescope for astronomical research, and do kind of everything Gemini North here. So I am an instrument scientist, which means I help with one of the instruments here. This is called the Gemini Near InfraRed Spectrograph. So I'm partially in charge of that instrument. That's one of the several instruments that we're potentially going to be using tonight. My job is sometimes to do the observing. Tonight, thankfully, I just got back from a 5-week trip in Europe, so thankfully I don't have to stay up all night and do observing. I can stop after a couple hours of observing. So tonight we have some very, very capable people in the control room. You can see them. I'll spotlight them now. So they're right behind Jamika. So Jamika's in the foyer there. And then we have, as Jamika mentioned, Charlie on the right. Charlie is our observer for tonight. We have Layla on the left. She's our operator for tonight, and we'll talk about what those terms mean. And then we have Denise on the far left there, and she's helping Layla with some of the technical aspects of the telescope. So in addition to myself and all these wonderful people controlling the telescope, we also have our wonderful IGRNS 2 instrument scientist here tonight, Haewon Soot. Haewon, would you like to say a word?
Hello, my name is Haewon. I'm a staff scientist like Brian, and I'm a IGRNS 2 project scientist here at Project scientist, right? Yeah.
When do you become instrument scientist?
Oh, okay.
Tomorrow?
Yeah. Once we accept it.
Okay.
So yeah, nice meeting you, everybody.
So we're in a special kind of night tonight. So normally, well, I guess it's not that different. We take ideas from all over the world, from scientists all over the world, and we pick out some of the best ideas out of those ideas, and anybody in the world can apply it to our telescope. And we put them all together in a pool, and on any given night, subject to the conditions in the sky and on the ground, the moon phase, we determine the most efficient use of the telescope. And so we normally do this with a multitude of different instruments, including the instrument that I helped to run, GNIRS. Tonight, we actually have a special kind of night. We're in the middle of a systems verification. Is that right? Okay.
Yeah.
So I know it is SV, and I never know whether it's science verification or systems verification. Okay, so it's very important that I say systems verification. And so the idea behind the systems verification is we have an instrument that's built by an external team. It's a Korean team, and I guess this is the first time the Koreans have built an instrument.
Yeah, and they're here.
Yeah, hello.
Hello, Kashi team.
Hi, Cassie team. So the instrument builders are here, and I guess we'll throw it over to them at some point to let us know. I know almost nothing about this instrument other than a little bit about what it does, but they know the intimate details of like how it was built and what all we're checking during this night. So the idea for the systems verification is that people, again, from all over the world get a chance to throw ideas to you guys, right?
Yes, the purpose of this system verification is to perform the end-to-end test using the Gemini operational procedures. So we accept the proposals using our system, and then we observe with our observer will observe the target, and our Q coordinator is this term. It's not so. Q coordinator is making the schedule for the SV target, and also we want to showcase our science cases in wide range of the science that we can do with the IGRINS-2 instrument. So that's the two main reasons to do the system verification. And we also, once the things are going well, then we're gonna offer it to the public officially. So we'll preparing for the corporate proposals for this IGRINS-2 instrument.
Yeah, so the idea is like we have a giant light bucket, which is the telescope. So like, cool, okay, we get all this light. It's an 8.1 meter aperture mirror. It's enormous. We get an incredible amount of light, and then we put that light into an instrument. And so we have a choice of which instrument to use. And each instrument has a different function or set of functions. And so like the instrument that I'm partially in charge of, it would be to take images in the near infrared, so further red than humans can see, lower energy light than humans can see. So it could take images in the near infrared. It can take a spectrograph, so it can disperse the light and then make a rainbow out of it. And it can also do something called integral field spectroscopy, which is in every point in the sky that it looks at, it can get a spectrum, so it can disperse, so it can get tons of different rainbows at once. It's for generally fairly faint things in the sky, a medium brightness to very faint things. So the kind of stuff that I study, which is very, very distant galaxies, is also stuff that Hwan studies, very distant black holes. And so GNIRS is an excellent instrument for studying those kind of phenomena. IGRINS-2 is also in the near infrared. It's what's called a slit spectrograph. So it's just a single slit, and then light comes from our giant light bucket, the telescope, to the slit. It gets dispersed, and it's very, very high resolution. So you can tell like blue and just like a little bit different blue apart. Whereas for GNIRS, you basically have in the near infrared, you basically have blue and then green and then red. So it's not like a fine discrimination. And so you're dispersing this light into very fine gradations. And this allows you to get very detailed information on fairly bright targets, because as you disperse the light on a finer and finer grid, you need more and more light to be able to achieve your science. So generally it's local stuff, and bright stuff. Although I think the plan is tonight to look at something very, very distant that is also super bright.
Yes,
and we may have,
Oh, okay.
I
was gonna ask how local is local?
Yeah.
I think local, I think of the island.
Yeah, right. Yeah. So we're looking in the probably in the local neighborhood, and local. All these terms are relative, right? Like you say, a young star in astrophysics, that could be 10 million years, right? Which is a long time for you.
For a human.
Yeah.
For a star, that's not.
Yeah. or a young galaxy. Like we can't even measure galaxies that are younger than 10 million years. Like we don't have the ability to do that. And so our time scale gradations in astrophysics are much different than our human time scale. So local neighborhood, it's the Milky Way. It's probably local stars in the Milky Way, which means, I don't know, 100 parsecs away, something like that.
That's about right.
Yeah.
For a back of envelope.
Yeah, so a couple hundred light years away. So a couple hundred times the amount of time it takes light to go 1 year, which that's actually a pretty far distance. So local is, not that local by our standards. It would take us many more times than 200 years.
How would it take you to walk there?
It depends on how fast you walk.
You say
Are you light?
The Olympics is about to start. If you were Usain Bolt, how far would it take you to get to this quasar? Or how long?
Okay, so he does the 100-meter dash in 10 seconds, under 10 seconds, right?
Yeah.
A long time. You'd get tired before you got there.
So this quasar that we're looking at, so if we're thinking as local as the Milky Way galaxy, how far off is this quasar that we're looking at?
Yeah, so that's a great, we just had another staff scientist join us. This is quite the party this evening. That's why we brought alcohol. Emma, would you like to introduce yourself and your quasar?
I'm not a quasar.
No, you're a lovely quasar friend that we'll be looking at this evening.
Introduce yourself as a quasar.
Okay, that's complicated. Hi everyone, this is Emma from just arrived. I had dinner. I thought it was nice. I work at Gemini with Brian a lot, with Yewan a lot, and I'm here to support the Shadow Scientist initiative for tonight. I don't know what I need to talk about quasar, but quasar are...
So we were just, we were introducing IGRINS too. We were saying like, okay, we got this giant light bucket, which is the telescope, and then we pipe it into all that light we take and we move it into an instrument. And so like GNIRS, which I know you're not very familiar with, but it's it's a imaging spectrograph. It has fairly low resolution. It can look at kind of faint to medium range brightness targets. But IGRINS 2 is dispersing the light much finer. And so it requires very bright objects. And so Emily's question, first of all, was like, how far away is a quasar relative to like the local stars that we're looking at?
on
They're about the same brightness, right?
No, it's not the same brightness. It's so what you a step back. The quasar we are looking at is actually, or the quasar I would like to look at, is on the other side of the universe. So if you imagine like like people, astronomers like to talk about things in redshift. That is a complicated concept, but it's basically saying it's called redshift 6.5 or redshift 7 around there, and may not tell you anything. But if you
so that basically tells you the number of times the universe has expanded since that light was emitted, right? And so +1.
But a better way to think about that is that how far away from the Big Bang this object is. So if you think that like, given that the light travels at a finite velocity, the farthest you go in time, the look more back. Well, the farthest you look at, the more far you go back in time, basically. And so basically, the idea is that when we are in the local universe, we talk about redshift 0. We're talking about objects that we see as they are redshift, right, as they are right now. And what the object they want to look up is on the other side of the universe, that is in units of billions of years, is something like 13 billions of years ago. So if you can imagine that, if you take the entire age of the universe, it's of the order of 13.5 years, billions years ago, 13.5 billion years. So basically, it's only 500 million years after the Big Bang. So it's like, it's really just after the Big Bang. You can translate that in human life. And if you say something that the entire life of the universe is the average life of a man, that is 80 years, 85, depending on where you live. So it's basically, if you're looking on an object that was created only like 8 or 9 years after the entire universe was born. So that's a unique opportunity because these objects are like extremely bright. So that's why we can do this experiment with IGRINS 2. And I like to try different things. So this instrument was designed to work on like, the main goal when the instrument was designed was to observe local stars and like close by quasar, close by objects. And I like to try to think what extra we can do with that. And then just going to the other side of the universe, I think it's pretty cool. In summary.
So it's a couple 100 million times further away than the stars that we're looking at this evening with Agnes too. Is that
Probably, yes.
something like that?
Yeah.
And so if they're like roughly of similar brightness, not to put you on the spot, I know you just ate dinner, but roughly of similar brightness, how is it that something that's, I don't know, a couple 100 light years away is the same brightness as something that's 13.5 billion light years away?
It's an extremely good question.
Well, thank you, Emma.
So what we define as quasar is that it is a supermassive black hole that you may be sort of familiar with. It's like this massive object that are black holes, but they have the size of like between 1 million and 1 billion times this size of our sun. So they are like the gigantic black holes. And like couple of years ago, they make the picture of the black holes. There are all these things. And the closest one that we have is one at the center of our galaxy. And the difference between this supermassive black hole and the one that we want to observe on the other side of the universe is that they are in a different phase. So the one close to the center of the Milky Way is a dormant black hole. So it's actually there, is not emitting anything. But the one that I'm interested in is actually what's happened is there is a lot of gas and a lot of stars that start to rotate really close to the black hole. And given that rotated, the friction make it like so warm, they actually start to emit a lot. And so it's like, you know, like if you like start to move your hand, you feel warm coming out, it's basically the same concept. But with the basic idea that instead of having like only 2 ends, you have something that is like 1 billion times our sun. And so you can imagine this get a lot of energy coming out. So this object became so bright that outshine anything that you can imagine. So they are so bright that are brighter than the entire galaxy that we live in. So if you take the Milky Way, like the galaxy we are, you look to the sky, and that's like, it's brighter than the sum of all the stars you see in the entire sky. So it's like, these are crazy bright objects. And that's why you can observe on the other side of the universe. Was clear enough?
I'm impressed.
Quasars are crazy and their magnetic fields are so gnarly as well.
It is a mess.
Yeah.
That's why we like to observe them.
Yeah.
Easy
Are there any
like-
local quasars?
Depends on what you call local.
I don't know, in the control room or over in Kauai or something?
The closest one is farther away than the control room, farther away than our sun, farther away of the center of our galaxy, but it's actually surprisingly close by. The closest object is actually was the first object that was found to have a redshift or to be outside our own Milky Way, and it was 3C273. That's a random number that doesn't mean anything for people that are not in the field. But this actually was the first object that was defined. Okay, we look to this object and we are 100% sure that it's not part of our own Milky Way. And so that's the closest object we have. And it's, I don't know, in units of this random unit that's called redshift, because I don't know the distance in any other unit. It's something like 0.03. And if you compare to the one that I'm interested in is 6.5, so it's like in this random unit is 1,000 times farther away. If Brian is calculating quickly.
Oh,
0.
you got the same idea. How much was the redshift?
0.3.
Around 4 billion light years.
Thank you. That's units.
So I just dropped a link in the chat to an image of quasar 3C273, so people can kind of get a look at it. And I think that was a fabulous explanation. Thank you, and I'm so glad you joined us, Emma. You were the missing piece to this whole puzzle as we got started. So now the team is complete.
And this is a new instrument that's checking out a quasar tonight, right?
If we are lucky.
Yeah, which we are going to be.
That's what I'm hoping. So how do we know if we are lucky or not? How do we find out about the weather and getting into the control room to learn more about what's happening right now?
Yeah, so I would pass that over to the control room because they have all the cool stuff to tell us what's happening up on the summit. And just for context, we are not on the summit of Maunakea here. We're basically at sea level in Hilo. at our base facility. And so we need lots of really high-tech gadgets to be able to monitor, and lots of really skilled people to be able to interpret those measurements and understand what that actually means for what we're going to be observing. So maybe I could pass to Charlie. Charlie, do you mind giving us a quick rundown of what you guys are doing right now?
Yes, rundown on what we're doing right now.
Wait. Oh, you unmuted?
I'm muted. We're good. So we are, hang on just a moment. We have started observations for the night. We started about 40 minutes ago. We're not in great observing conditions right now. We over the course of the evening, we monitor a number of environmental conditions at the summit. So we monitor how much cloud cover we have, how much attenuation clouds will absorb starlight. So we monitor how many clouds, how thick those clouds are. And we choose different scientific observations as a result of that. We monitor what we call seeing, which is how clear the sky is. When you look at when you look at a starry sky and you see lots of twinkling, the stars, you see a lot of twinkling in the stars, that's atmospheric distortion. And sometimes that distortion is very small and sometimes it is much larger. Often if you're in a part of the world where it gets cold in the winter, you may notice that the stars appear much clearer. They won't twinkle as much on a nice clear winter night. The air quality, the seeing is better in those conditions. Right now, our seeing is pretty poor, which means we have to choose a certain set of observations, that we can observe. And so we're kind of working down that list, trying to find things that will fit the current conditions, the current sky conditions that we experience right now.
Charlie, could you talk a little bit about what your role in particular is this evening?
Sure. So the standard team for our night crew is to have an observer and an operator. And we definitely have very different roles, although we work together very closely to make the observing happen. As the observer, I'm in charge of the science program for the night, basically. So I'm going to look at the environmental conditions. I'm going to choose from an available list, or several lists actually, of observations that we can conduct. And I'm going to be watching that, changing that plan moment by moment. Sometimes on a really rough night, it's moment by moment, in order to get the best science we can for the weather conditions that we have. The observer is kind of the director of the show. We're kind of this is, we're in charge of everything that's going on, basically what's going on with the science aspect of telescope observing of the operations. Leila, would you like to talk a little bit about operations?
Yeah,
Sure.
if you don't mind, Leila, just give us a quick rundown of what your duties are over there.
Okay. Hello, everyone. My name is Leila. I am one of the newest telescope operators here at Gemini, and pretty much, from what I understand so far, the observer has the plan for the night and has all of the information, and I am in charge of slewing the telescope based on the observing program so that we can guide and we can take that science. And then I'm also in charge of the health of the telescope. So whatever errors that happen, whatever instrumentation fails, or things that come up during the night that prevent us from doing our science, that is my primary duty to help guide that. Yeah.
Awesome. Thanks, guys.
Yeah, sure.
And so, I mean, all three of you you take on different roles in different nights, right? So Charlie, for example, you could be over in the operator's chair. So you all have the expertise to you
It's
all
occupied, but I could be.
you have the you have the expertise to sit in both chairs.
Sure.
Whereas for us, we're mostly on we're completely on the we're confined to the right side of the room.
You are confined.
Yeah.
Confined is the right. We don't trust you in the other chair, Brian.
There's the laser fencing over the in between. So let's see. Is there do you have a TSD up? My TSD isn't working. Do you have a TSD up?
I do have a TSD. If you have got a keeper, you can look at LD. If you can look at LD1, I've got it on screen 7.
And
Right,
Brian,
okay.
really quickly before we go to the TSD, I'd like to invite Denise, who's also in the control room, to introduce herself if she'd like.
Hey, I'm Denise. I'm on operation duty so right now Layla's in the chair because she's on training. But I am here to provide any guidance if it is needed, but she's doing great.
Excellent. Thank you,
Good teamwork.
Denise.
I just want to mention again that this is really a teamwork, and like most of the night things go super smoothly, but some night we have hiccups or like issues and everything. And it's always incredible how many people can help us at any time to make sure that we can get to collect the best data we can at any time possible. And so, for instance, like for the items that we are in this situation, it's called system verification. So we are checking that everything goes well. And if any hiccups, like people from here, people from Korea, people from everywhere in the world actually jump in to make sure that things help, the things work properly and provide all the knowledge, all the help, or everything possible to make sure that we have the best data possible on the telescope, on the disk. So that's always incredible for me. Every single night, something bad happens. It's like people jump over, say, no, I help you. We solve this as fast as possible. It's always an incredible night.
Yeah. Yeah. And I think that's a very good liaison for us to go to Korea, because this truly is a worldwide endeavor. So we have two Gemini telescopes, one in Chile, one here, twins kind of, but have different capabilities. We have partner countries that contribute in various ways and also use the telescope in various ways. So the CASI team, who's here tonight, developed this capability that we're using this evening and testing out this evening. Before we go over to the CASI team, I noticed there was one question. So it was from Eric, and it was about when the seeing is poor, what type of target makes a better candidate for observation? That's a really good question.
I'm wondering, like, how poor is I'm sure it's different based off
Yeah.
of, like, exactly how poor the seeing is.
Yeah. So we have pretty precise measurements of the it's called the seeing. Basically the blurring of a point source in the sky, and effectively infinitely small source. So a star, which is very big when it's viewed up close, when it's hundreds of light years away, is infinitesimally small. And so it's the blurring of the infinitesimally small object. And tonight, I think, Charlie, you were measuring something like 1.4 arc seconds for the seeing.
1.4 for a good, one of our better measurements. We've been seeing some 1.7, some measurements over 2.
Okay.
So that's not really good.
So we have some laughing in the back here, and that's indicating that that's maybe not the best conditions that we could have.
Especially for Maunakea. Maunakea has really excellent seeing.
Yeah. But just to give people...
I was going to add, to give you give our viewers a sense of context, we measure our seeing in arc seconds. If you think of this is an angle, basically if you imagine a triangle drawn from one side of an object to your eye to the other side of the object, this really thin triangle, what's the angle of that? And when we're talking arc seconds, we're talking well, your fingertip at arm's length is about 1 to 1.5 degrees wide. An arc second is 1/3600th of that. So if you imagine breaking that up into 3,600 parts, one arc second seeing, that's how much it is. And that's not great seeing for us. We're really happy when we get down to about 1/3 of an arc second seeing. 1/4 of an arc second seeing is about where we really like to be. So at 2 arc second seeing, the stars look like big blobs in our detectors. So
Again, but that's still 1/1800th of a fingernail.
that's still 1/1800th of a finger width. Yeah, your finger width. Exactly.
Yeah.
To human eyes, that's
yeah.
but to a telescope eye.
But Eric, you're right. It's a magnitude related situation. So in the end, if you're blurring out a source more, and you have a fixed size for your slit, as you do in IGRNS 2, so it's about 0.3 arcs, right? Then you're start losing more and more light, right? So when something is 2 arc seconds wide, roughly you're only collecting, it's not a uniform disk, but roughly you're only collecting about 1/6 of the light of that source. And so the brighter the source, the better in that case. Now there are instruments like GMOS or GNIRS that have adaptable slit widths. And in those cases, or an integral field spectrograph where you can look at a field, a portion of the sky where you don't have to worry about that light dispersing outside of the slit. And so you can adapt your observation to the conditions. So we have like fairly strict conditions for each program. It says like, okay, a scientist would say, I can't accept any worse than 1 arc second seeing.
It looks like
But sometimes we call up those people and we say, hey, well, it's 1.1 tonight. Maybe you could think about like making your slit a little bit larger and you still collect the same amount of light. Maybe you lose a little bit of resolution. They say, yeah, okay, yeah, go for it. They're usually drunk, but yeah. But the idea is that none of this is rigid. I mean, we always adapt to the conditions, and we try to make the best observations possible.
Good.
And so, yeah, usually brighter is better, but sometimes you don't have that option.
Right.
Things are as they are.
The 2-minute time loss.
Like actually really don't mind.
The time loss.
So put it.
Potential time.
Put it.
We have what is called bad weather programs. Poor weather programs. That means that we can collect scientifically relevant data, even in the condition that not the best we can have on Maunakea. So one example is like, if you want just to know the total flux of a source, and you do just imaging, so you take a picture of the source. Actually, it doesn't matter how big the source is, as long as you have enough signal to measure what is the total, the sum of all the lights that come out from the source.
Yeah.
So in that condition, is basically you can do an experiment where I don't mind how big the source is in the sky. I just need to collect all the data is there.
It can be helpful actually
Yes.
sometimes. So when you have like really faint surface brightness features, for example. So there was a program I was helping for next semester, which is looking a detection experiment on what looks to be a fairly dark hydrogen cloud. And so they actually ask for what we call IQNE, so poor seeing conditions, because it actually bumps up the signal because it just kind of blurs everything together. And all they want to know is it there and how bright is it? Mm-hmm. So it's not necessarily a bad thing.
In some condition, there is also the other parameter we monitor, that is the cloud cover. And that's much, much more tricky. So for spectroscopy may not be such a big issue having that. But for instance, in that case, for imaging, sometimes it's so cloudy that you cannot actually see anything. And so as you can imagine, if you don't see anything, it's not a good night. But there are conditions that even in this situation, you can still collect data that are useful scientifically. And so you always cut, that's what we are doing here. Like what part of Charlie roles is adapt the plan of the night according to the sky condition. And now we always have the most relevant scientific data based on the condition you have. And so we really rarely throw away a night, only if the conditions are so bad we cannot really open, or it's snowing, or it's raining, or something like that. But most of the time, we always have something interesting to be observed.
Brian,
Yep.
Emma, Emily, everyone in the control room, we're treated to usually amazing seeing, as you were talking about, but on the mainland, what is the average seeing conditions? Is 1 arc second, maybe 1.4? Would that be acceptable to for some telescopes on the mainland, depending on the aperture?
Yeah, it really depends on the location. So I've been in a couple of telescopes in California. One that has been featured on many Shadow Scientists nights, which is the Shane Telescope on Mount Hamilton in San Jose, California, otherwise known as the Lick Observatory, or one of the telescopes of the Lick Observatory. I was doing a project during my graduate studies where I think, it was 4 or 5 nights in a row that we had, and we were getting seeing around 2 to 2.5 arc seconds. And the operator was actually kind of impressed at how good the seeing was on when we dropped below 2 arc seconds. And so that's just, it's all a sense of scale. And so like, it's all relative. Palomar is another telescope that I've used in the Grover Cleveland National Forest in Southern California. There also the seeing is generally in the neighborhood of 1.5 to 2 arc seconds. And so we did a lot of imaging studies with those telescopes. And there, as Emma said, maybe you're just interested in the brightness of an object, and you don't care so much if it gets blurred out. We're not trying, in my particular case, we weren't trying to pick out like fine features of a galaxy. We were just literally trying to measure the brightness and then follow that up with one of the a set of interesting set of galaxies with one of the Maunakea telescopes. And so, yeah, but there's, you could say mainland in South America, Cerro Pachon, where our sister telescope is, there the seeing is fairly similar to what we have here. And a lot of it has to do with the topography of the land, the way the climate is, how the wind comes in, where it's situated relative to the ocean, all these different things. So that telescope is in basically the Atacama Desert. And so it has a very nice laminar flow of wind, just like on Mauna Kea.
And even pollution can play a factor. Whenever I think about bad seeing, I always jump back to the Griffith Observatory in LA, which used to be a great site 50 years ago for astronomical viewing. But one time I went to visit and I saw like a film from an observing night that they did with some amateur astronomers that showed the moon, and the moon in the image was going like this. And it was like my brain just exploded. It's like, that's like the worst thing that I could possibly imagine.
Yeah.
And that's pollution, that is harsh wind currents, that is so many factors coming together.
And the pollution hurts. I mean, with all the capture of like greenhouse effect, it makes conditions much worse in the ground, creates more eddies and ground layer turbulence. Another issue is light pollution. So like urban creep in San Jose and in Los Angeles, Mount Wilson also is another observatory that's very famous, where some of the first redshifts were ever measured. And that's, it's still a working observatory, but it doesn't do what it did 50 years ago or 100 years ago.
In other words, there is a reason why we are in the middle of the Pacific, on the top of super high mountains to do these experiments. It's not
the beaches.
Yeah.
It's not the beaches.
Okay.
Mauna Kea being a shield volcano in the middle of the Pacific Ocean, the air moves very stably over the Pacific Ocean, and then the steady slope of the shield volcano means that air is moving very, very smooth over the summit of the mountain. And then Mauna Kea is also 14,000 feet above sea level, which makes it's the tallest mountain in the world if you take the entire mountain from the base of the sea floor. But it's reaching high enough into the atmosphere that there is significantly less atmosphere between you and outer space, which greatly reduces the scene. And also light pollution. There's not a lot of extremely large population centers close that we're having to interfere with all of these other factors.
We're only 6 hours flight away from Los Angeles.
The pollution can't get us from there.
In the chat, you all, I dropped a link to where you can learn more about the different types of programs that are being observed for 24B. Those are band 1, 2, and 3 programs. And that really relates to weather is one of the factors that helps to determine the band. Maybe one of you could speak on that, and then we could head over to the CASI team.
Sure, yeah. Yeah, so, I'm happy to talk about the bands. So the bands, this is on a normal, normal night for us. So not during the systems verification, but during a normal night for us, we would have this big pool of observations, and those observations are scientifically ranked. And so band 1 would be like, okay, those are the best ideas. Those are the ideas that we like absolutely have to get observations for in a given semester, because we break up the observing just to mark time. Then mark the passage of time. We break things up in different semesters. So in a given semester, there's probably, for Gemini North, there's probably something like 20, 25 band 1 programs. And then we have band 2, which is a little bit lower priority. It's still really great ideas, but not as strong of ideas as the band 1 programs. Then band 3 is the natural extension of that, a little bit less quality. And this is all peer reviewed. So scientists from all over the world read proposals for time on the telescope. About 10 to 20% of people that propose for telescope time get it. So these are the best of the best ideas. So band 3 doesn't mean you have a bad idea. It just means your idea is in the, it's still in the top like 92nd percentile of all proposals that were submitted. So it's still very good. But it's just hard. I mean, this is a big telescope. It's, it's very valuable. Astronomers all over the world want to use it. And so this is, it takes a really good idea to even get on band 3. And so, Jamika, when you mentioned about weather, the relationship between bands and weather is usually when your scientific idea is ranked a little bit worse, then you would say, well, I'll accept a little bit worse condition. If your science can handle it, I'll accept a little bit worse conditions so that I get a better chance of my my observations taking place during a semester.
Excellent. Thank you for that explanation. Because I really like seeing everything here on this page, because you can see which programs have been observed and what are the ones that are still in progress. So if they're still in progress, does it mean that the program just stays in the queue, and then when time or conditions allow, then you observe it to completion if there's time?
Yeah, that's the hope. That's the hope. So we're actually coming to the interface between 2 semesters in 8 days. That'll move, we'll be moving from the 24A semester to the 24B semester. And at that point, any program that's not completed, that's from 24A, that's band 1, that will roll over to the next semester. Band 2 programs, band 3 programs do not roll over. So the idea being that the best scientific ideas, we'd really like to complete those. Those are the highest leverage observations, and we sometimes get to 50, 60, 70%. And we found that completing a program makes it much more likely that a program, that good science will come out of that program. If we get 50% of it done, it makes it much harder for the scientists involved to actually get a usable result. Because a lot of times when we're proposing, we say, no, we need these observations, because if we don't get all of them, then it makes it very, very difficult to interpret, what we're getting. So sometimes we ask a little bit extra, but most of the time we're asking for what we need. And so if we only get half of what we need, then it hurts in terms of our ability to make concrete conclusions, and even in our own mind lend credence to our results. Oh, yeah.
Yes.
Yeah, no problem. So yeah, I think this is a great time to move over to the CASI team to talk about what the instrument that we're using tonight, if they would be so kind as to let us know a little bit about the instrument.
I don't think they will prepare for the talk, but
if you guys don't have anything
I'd be
prepared.
nervous. But Young, can you talk about the IGNIRS too?
Yeah, thank you for introducing us. Yeah, in this room, actually 3 members are sitting here in the same room. So yeah, I wanna give the first chance to Chambak is our instrument PI. The Kashi team, the algorithms, the builder PI. So he's sitting in the far side of the table. So maybe.
Okay, I would like to just introduce ourselves. 안녕하세요. Anyone can understand this greeting? It's hello, hi in Korea. 안녕하세요. Okay, everybody is mute. So.
Oh, yeah, we can hear you. We can hear you.
Sorry.
Okay, so let's go ahead. So we are the instrument development team in Kasi. So recently we developed the instrument called iGNIRS 2. It's the second version of iGNIRS. So actually the previous version, the original iGNIRS was operated in Gemini South in Chile several years, but now it is moved to Texas, Austin for maintenance for next operation. So after using that original iGNIRS at Gemini South, Gemini thought that it will be useful and it will be good if a facility instrument, a permanent instrument at something like iGNIRS in Gemini. So about that time, few years ago, Kasi joined as a regular operating partner of Gemini International Observatory. So with that chance, Kasi decided, Kasi and Gemini agreed to make some similar another version of iGNIRS. So we call it iGNIRS 2. Actually, we tried to make a proper name of this instrument, but surprise, still we just call it a project name, iGNIRS 2. So it is basically a instrument, high resolution instrument spectrograph. So in Gemini Observatory so far, there is a few mid resolution. Well, I don't know if you, I think most of you understand what is the mid resolution, low resolution, and high resolution means in spectrograph. So in Gemini, there is many excellent instruments in Gemini before, but they are not high resolution instrument. So in infrared, Kasi wanted to provide the high resolution spectrograph. So last 4 years, we developed that instrument, and then from last October, we started to get first light from skylight. So so far, Kasi team visited 3 times in Gemini North, and it was quite successful. And currently, today, actually including today, it is 4th time of the test observation. So hopefully it will be the last test observation. So we call it a science verification run. So if it is successful, then it will be open to the general community for the scientific research. Okay, let me talk about just a little bit of this instrument. The most property, the biggest property of this instrument is the way how to make the resolution high. So that is due to the special optical element called immersion grating. So this immersion grating is the grating is the dispersing the light, the mixed light will be dispersed with several kind of spectrum of light. You know that? So the degree of dispersion, we call it resolution. So to make the resolution very high, the immersion grating, the eye-grains use very special optical element called immersion grating. So I think if you are interested in this special aspect of high resolution immersion grating, then I think you will have a next chance to get approach this aspect. It is very interesting and very exciting area of astronomical spectroscopy. So let me just pass this introduction of instruments. So if you have any question or any comments, then please go ahead, and let me hand it over stage to Hyung and Jiyeon for introduction of herself.
Okay.
Okay.
Yeah. Thank you. Yeah, thank you so much, Chan. Yeah, thanks for all the introduction. So yeah, Chan talked pretty much, so I don't have anything to add to the instrument itself. So I'm Hyung. So I served as a systems engineer during the development during this project. So yeah, we are very great. We feel really happy that we are kind of the final stage to deliver this new instrument between the collaboration between Kashi team and Gemini North. I mean, Gemini Telescope, both South and North. It was really nice collaboration. So yeah, we are exciting to be almost prepared to be open to the astronomical community. Maybe, hopefully, end of this year, we can get started to open for the community. Yeah, that's short. So, yeah, maybe, yeah, Jiyeon can introduce.
Hi, everyone. Unfortunately, I'm not a team of the eye-grains, but I'm a member of the Korean Gemini office, which is basically to support the Korean users from like the preparation of proposal to the observing preparation and the data analysis. So I'm happy to be here to join the Shadow of the Scientists, and thank you.
We're actually so glad to have all of you join us for this session, and we do hope that you'll join us in future sessions, especially when we are featuring eye-grains 2 when it's open to the community. A question on immersion grading. How is the grading manufactured? Is it using a metal cutting laser?
Traditionally, conventionally, making the grading is just cutting, grinding out glass. But this is some special method. The material is silicon. So the silicon is the fabrication of silicon is a very well developed industry in semiconductor industry. So they know the semiconductor industry, they have very sophisticated way to deal with the silicon. So we use one of their methods. So we call it masking. We first make a very thin mask, and then we use a photo. What is the name of the lithography? Photolithography method. So we use special material, and we use ultraviolet light to melt. And also we use etching method, a special chemical material and deep in the chemical to melt out the atom of the silicon very slowly. So you can find out the lithography of silicon. Then you will be reach how to manufacture this element, immersion grating element.
Perfect, thank you. One of the things that I personally love about science and astronomy in particular is that it's such a collaborative effort. And this team, Gemini, the International Gemini Observatory in particular, is a fantastic example of that. And so what was it like? How did you, what are the logistics of working with such an international team to not only come up with the concept for a new instrument, but to actually start working on it, build it, and then now be in this verification process?
Yeah, I think I also it is the first experience to work with Gemini. So we found that Gemini itself is international observatory and international institute. So it looks like they are very ready to be working with international partner. So we felt that we, as a Korean, we felt that it was very pleasure to work with Gemini colleague. So they were, thank you. They were very ready to support international partner, and they were good to work, easy to work. So I think if we have another chance, I hopefully work with them again.
I love that. That's amazing. That's amazing. We knew that the Gemini team was super stellar, but you've definitely confirmed it.
Mika, I'd like to ask our two staff scientists here that worked with the CASI team throughout. I mean, Hwan, you've been working the CASI team for a long time, but with IGRINS too for a couple of years, right?
Couple of years now, yes,
Yeah.
1.5 years. So I visited CASI and CASI team visited us. So
yeah, but like kind of like what was your role? And I mean, it's slowly the instrument is so CASI built it, and they built it for a reason, and they they had scientific interests, and Gemini also had scientific interests that were similar, and so the instrument was built. It was designed, built, shipped, and it comes here. It's now on the summit of Maunakea. What is that interface process like? Because I mean, we're now taking responsibility of it, right? I mean, we're kind of in the the transition phase, the in-between phase right now, and so it's kind of what are we looking for tonight and throughout this process, and at what point does this become your guys' responsibility?
So CASI team built this instrument and then bring to us, and then now we want to have it our facility instrument. So we want to test with our software, our procedures, and with our staff. So we want to learn from them, and this is transition phase. So now we're working together to make it work, to work at the Gemini Observatory. And finally, we can offer to the Gemini community to use this instrument. And can you add something else?
I mean, so there's all these technical aspects, because Gemini has certain requirements, right, that are bespoke in a document, and so we need this focal length, we need this size, we need, it's actually mounted on the back of this weight. It's mounted on the back of our telescope in our cascading cage, so it can't be 20 tons, blah 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 blah. But we also have software needs, right? So it has to interface with our software in some way. And there's, both like post-processing software, reduction software, archival software, all this kind of stuff. All of that has to work. And so we're at the interface stage of that, but also this systems verification. You guys are pushing the instrument, right? Like, so it was designed for certain types of science in mind, but it's very rare in any astronomical endeavor that people say, oh, okay, that's all we'll do with it. You design something and you have some good ideas in mind, and then some really brilliant person or brilliant people come along and say, actually, let's use it for some other random thing. And so that's part of the thing that you guys are doing right now, right?
Yeah, I think the entire process is like, is much more a continuous interaction and feedback between different groups. So it's not that it didn't work the way that like Kazi built the instrument, ship it to us, our engineer take it, plug to the telescope, me won't test it. That doesn't work that way. So we have
it is sufficient.
Yes, segfold. The process is long, so the Kazi team did an excellent job, and proceeding with that, we start to interact with us more and more. Like once you start, Gemini has some requirements for the, as Brian said, from the size, from the focal length, from the weight, for like all the properties of the instrument itself that need to be fulfilled, simply because otherwise we cannot attach it to the telescope. But then from that stage on, there is a lot of things that needs to be agreed upon at different level to arrive to the final product that everything works perfectly. And it's like, there are constraints given by the engineering side, constraint given by the software side, constraint given by the science side. And so all this is a continuous discussion, like what is the best approach to arrive to the end, to the final results. And so that's what Chan was saying. It was really important for us to have the Kazi team visiting us and for us to visit the Kazi team, because there was a point of interaction, like in-person interaction, what's the status, what the stage, what we can improve, what we can provide to the Kazi team, what the Kazi team can provide to us. And it's like, it's not us, it doesn't mean me and Yewon. It doesn't mean that 4 people here or everything. It's like there are software engineering, there is actually the real engineering. There were the people that work on the summit to attach the instrument telescope. The Kazi team, when they visit, they spend like a week up to Maunakea. And if people are not used to stay at 4,200 meters, so I don't know what is in feet, but it's really high altitude that is extremely impressive that people are able, like, they work hardcore for like weeks to make that happening all the time, in the right amount of time in the perfect things. And so it's this interaction between people, this interaction between different groups, this international interaction allows us to arrive to the end users at our user community. But we arrive there step by step with continuous interaction, continuously providing feedback, arriving to the final point. And now we are really excited about the system verification, because as you can imagine from the name system verification, we are verifying that this 4 or 5 years process, discussion and everything, now brought a result that actually produce magnificent science on the sky. So that's why we are really happy that this is happening.
So the
We're
difference, sorry.
Go ahead, please.
The difference from iGNIRS and iGNIRS 2 is the instrument itself also some different, but the iGNIRS was the visitor instrument. So the responsibility for that instrument maintenance and operation was in Kazi and UT, University of Texas. It is a joint project. So, but iGNIRS 2 is will be facility instrument of Gemini. So that means the maintenance and operation and all the ownership and responsibility will be in Gemini Observatory. So that's why now they are doing the science systems verification learn on their own. I mean, Kazi have to transfer everything we have to Gemini. So later, Gemini staff need to operate it themselves. Of course, CASI will support if there is any technical issues, CASI will support it, but basically the ownership and responsibility is the role of Gemini. So that's the difference.
Yes.
That's definitely quite a difference from a visitor instrument to a facility instrument. So thank you for explaining to us what a facility instrument is. Is there a way we could maybe see what iGNIRS 2 looks like? I believe there's maybe a diagram or a schematic on the verification page, maybe?
Yes. Because of the weather condition tonight, we will start the iGNIRS 2 observation around in an hour. So
There.
Hey, who's that? Are we sharing screen?
No.
Okay.
Sure.
Can somebody share?
Hey, who's that?
Oh, good. Aw.
That's who.
So that's Haywan.
Yeah.
She's here and there. What else do we have to show, guys? So this is the Gemini website, and on the Gemini website, we have all sorts of cool stuff. We got all sorts of cool outreach stuff, all sorts of cool things like you can sign up to like come to our base facility. You can sign up to like go to the top of Maunakea and look at our telescope. You can propose for time.
Mm-hmm.
And on top of that, you can look at all of our current instruments. And now iGNIRS 2 is a current instrument here. Yay!
With the red banner means not
Aw. And then we have future instruments, ones that are coming, also iGNIRS 2.
because it's
So this is truly in the
Train.
transition phase. So
Future as in an hour.
so at the end of this SV, hopefully this is gone from the future instruments. So I guess this is the schematic that so this is actually iGNIRS 2, right? This is what it looks like. So this is the bottom at our telescope is the bottom of our telescope is here. This is our CAS cage with all of our instruments. This is the bottom port of our telescope, right? So the light is basically just pipes down. Actually, I can bring up
The yellow thing.
Okay, so here we are. So this is something we mentioned earlier, which is called TSD. It's a telescope status display or systems display. I don't remember which. And it's all sorts of, this is one of 8 screens. I'm now sharing one of Charlie's screens. So Charlie has 8 screens. Layla has 8 screens. So it takes 16 screens to run a night on Gemini, and
never enough.
yeah, never enough. And so I actually normally bring in like multiple other computers to look at other things. So it's crazy. So there's tons of information here, including where we're pointing at the sky right now. I think we're just we're running some telescope calibrations, getting things ready for later. But so this is a schematic here of our dome. So this is our shutter here for our dome and where the telescope is pointing. These are various cable wraps that we have for the telescope. And this is a kind of 1980s depiction of what the light path is for the telescope. So 1990s, okay, early 1990s depiction, Clinton era depiction of what our light path looks like for our telescope. So light comes in from the universe, whatever we're looking at, bounces off our primary mirror here, goes to our secondary mirror, bounces off the secondary mirror into a hole in our primary mirror, purposely made hole, as opposed to accidentally made holes.
It's good to distinguish.
Yes, those are very important to distinguish. So there's actually a tube here that the light is sent through to our deployable tertiary mirror, which we lovingly called the science fold. And that pipes light to one of our many instruments or many instruments within the CAS cage. And so iGNIRS 2 is here down at the bottom port. I think we were just doing some high resolution wavefront sensor works. So there's yet another mirror down here. But if when iGNIRS 2 is in use, we'll undeploy our deployable tertiary. We'll remove this mirror and we'll just send the light down to the bottom where iGNIRS 2 is. And so that's what this is here. Yeah. So light just comes in. Yellow stuff. Okay. Not this yellow stuff, this yellow stuff. And then this is the guts. So anything you guys want to talk about in here? It's a pretty complicated looking diagram.
Can someone, maybe break down the diagram a little bit?
You wanna do it? 또 가요. 설명. So yeah, Chan can do it. Yeah.
Okay, that would be great because we're getting a lot of enthusiasm here.
So I'm not sure what kind of audience we have today. So let me just go ahead just in general. Okay. So this is, we call it optical design. So optical layout. So I forgot everything about 20 or 30 number of optical element iGNIRS is using. So you can count it. But here we have telescope focus. So this is imaginary surface. So telescope will collect the 8-meter telescope primary mirror light will be focused on this position, this point, and from this point, iGNIRS instrument optical design start. Here, right. So it is about 4 centimeters outside of the iGNIRS chamber. iGNIRS have about this size of rectangular vacuum chamber. So the size, the length is about 1 meter. And basically, iGNIRS is the infrared instrument. So we need to make every element, optical element, make cold about minus 200 degrees. So to make that low temperature, if there is any air, then the water vapor will be condensed and frozen the surface of optical element. So we cannot make it. So before we make temperature lower, we need to make vacuum the chamber. So we made a metal chamber and make it at very good high level of vacuum, and then make it cold up to minus 200 degrees. That's because since this instrument is infrared, so if we don't make it cold, this optical element itself will be the source of light, source of infrared light. So it is not effective to observe the celestial object infrared light. So we want to make it as low as possible background noise. So that's why we need to make this optical element low temperature. That's the first principle of infrared instrument. Okay, and light come through this way. So here is we call it input optics. That means telescope light will be converted the F number. That means well, F, I don't know if you're familiar with F number, but that's the angle of light converts. So with this input optics, we can use different telescope. If we want to use another telescope, we want to change this part of design to match that telescope light. So with any telescope, this part, the spectrograph part, will be identical. Will be operated. Can be operated in with any other telescope. So this input optics. So we also can say that F converter. So the light from telescope can be converted F number 10 in for the spectrograph slit. So this is the slit component. If you see in front of this slit surface, it has, well, actually it is rectangular, but at center it has very sharp rectangular shape of a hole. So through this slit, telescope light get into this optical system. So light get into this way, and here is a small mirror, and the fold mirror. The folded light goes this way, and here we have a collimator. It is a parabola. It's kind of telescope. The diverging light will be collimated at this mirror. So this mirror collimates light to grating. This part is immersion grating. This is immersion grating. So inside this immersion grating, there is a step. You know the grating. There's many a groove. So through that groove, light will be dispersed or diffracted. So that diffracted light come out again through this way, and this light will be reflected this collimator again. So this collimator will be used twice. Then that reflected light goes through this way. So here we have another component, dichroic. Dichroic means divide the light two sections. One section will be transmitted through dichroic, and the other section will be reflected at the surface of dichroic. So that the division will be happened about 1.8 or 1.9 micrometer. So the shorter wavelengths will be reflected, and the longer wavelengths will be transmitted through this dichroic. So that means we have two parts of light. shorter wavelengths, the reflected shorter wavelengths goes this way. And here we have another collimator. We call it pupil transfer. The function of this pupil transfer is making light collimating again, then reflected a flat mirror. And here we have another grating. So it is low resolution grating. We use it VPH grating. That means the grating with the transmission and diverse dispersion at the same time at this VPH grating. So the function of this VPH grating is for the cross dispersion. That means usually when we make a spectrum, it will be one-dimensional, but iGNIRS, it is a two-dimensional spectrum we have, something like this. So that is just for better use of all the surface of detector. So conventionally, we when we use the prism, we can just use one line of spectrum. But these days we have this rectangular shape of detector. So if we just use one line of spectrum, then the other part of area it is useless. So we designed the cross dispersion method. So that means iGNIRS use about 20 line of or 20 order of this spectrum. So we can use most area of the detectors to see the information, the stellar spectral information. So we have two channels. One has H channel and one has K channel. So in H channel, we measure from 1 point, let's say 1.4, 1.5. Yeah, roughly 1.5 to 1.8 micrometer. And in K bands, we measure about 2 to 2.5. Sorry, 2 to 2.5 micrometer. So in astronomy, we just call it H band and K bands. That is the just the area of the range of the wavelengths. So based on the atmospheric windows, the atmospheres have windows J, H, K, L, M. That means some range of wavelengths only transmitted through Earth's atmosphere. So if we go out of atmosphere, we will see a continuous light. But in Earth, on Earth, because of the atmospheric absorption, we only see some range of wavelengths. That's we call it atmospheric window. So from that window, we just use in iGNIRS we use H window and K window. That is roughly from 1.5 to 1.8. It is H window, and from 2 micron to 2.5 micron, it is the K window. That is the iGNIRS is working wavelength. Okay. So this is the brief idea of how the algorithms is working in optical link. Okay.
That was an absolutely amazing, detailed explanation of
Sorry,
what we were saying. It was fantastic. No
But I am not
apology.
ready to explain.
You did a great job.
Absolutely. I'll take it back over to Brian, Heywan, Emma, and Emily for some follow-up, maybe. Oh yes, we have spectra. What's going on?
Yeah.
So at the end of that entire process, this is what we get out. So I'm gonna let the experts tell you what you're seeing here.
Which target is this?
This is a star.
Yeah.
So this is part of our calibration suite. So basically, this is the spectrum of one star specifically. In the left side, you see the H band. In the right side, you see the K band. So that was Chen was mentioning that the bluer side is on the left and the redder side is on the right.
But just to give people like a sense of scale. So H band, as mentioned before, it's like 1.6 microns, right? So this is twice as red as we can. So what you're calling blue or light is twice as red as we can see with the human eye, right? So we can see up to about 0.8 microns. But depends on your capabilities, but 0.8 microns. So yeah, twice as red.
And the right side is 2.2 microns, so it's 2.5 times as red as we can see in your units.
Pretty red.
So here the thick line is from starlight, and the thin line atmospheric air glow light. I think it is worthwhile to explain it.
Yeah. So the idea is that whenever we observe a target in the sky, then we want to have a reference to make sure that autocorrect all the effect of the telescope in the atmosphere from the target. So we take one bright star that we know exactly the spectrum I should look like, and then that's what we are taking here, and then use this spectrum as a model to make this is the real value we expect to get, and then we can correct at every single wavelength. This is the total flux we expect. We have a correction for that. This is the difference of the absorption of the atmosphere that goes and like dim the level of light, and then we can correct for that. All this kind of thing.
Wait, how do you know what it's supposed to be? Aren't you observing it to like find out?
These are the specific stars that we exactly know what the spectral shape is.
Because you're super smart, or what?
Because yes, I like this answer. So if you need to know the spectrum of a star, just ask me. No, basically there are two ways we know about that. On one side, for some of the stars, we actually have spectra from space. So we know we remove the entire atmosphere. We go to HST or to other what's called Gaia or other like satellites that can take spectra, and then all the effect of the atmosphere removed. So we know the true spectrum, how the spectrum of the star will look like without atmosphere. And the other way that people that are much smarter than me actually figure out the way the emission of a star at such a high level, they can make prediction on how the real spectrum of a star would look like. And so they create models, and through this model, they can say, okay, given this star have this color, this temperature, this surface brightness, this gravity, and everything, they can give me the perfect model of this star. And so that's why we know that. So don't ask me, ask people that really know what they're doing or how the intrics is spent. So you can see that, so there are two things that are important to see here. You have several lines that goes from the top, from the bottom, and they're all the same object. They're not different objects. These are the same star observed. And that's what the combination of the dispersion gratings and the algorithms does, that actually spread the light in so many different channels that there is not enough space on your detector to put it on a single line. So you have to pack them up one after the other, one after the other. It's a sort of rainbow way.
So the immersion grading disperses light left to right,
Yes.
and the VPH grading disperses light up to down.
Right, that's right.
And so in this way, we can pack much more information in the same detector. And the other things that is important to notice is that the slit or the drawing the channel before this, like the slit viewing camera with a hole in the middle, the slit is exactly the size that you see from the top of on the bottom of one single of these rainbow arches. So that's the size of the slit. So that's the spatial resolution you can have on your observation. And so all the vertical lines you see are actually skylines. So emission from our atmosphere that can be used in two ways. So basically, we know these lines really well. And so we actually use that to cross-calibrate the spectrum in wavelength. So given that we know exactly every single one of these lines where it is in the spectrum, we can say, okay, the top left line is 1,593 angstrom. And we say, okay, that point is 1,593 angstrom. And then you keep going for the entire line list. And then for every single pixel, you know which wavelength you are. And that's really useful. And actually, we use that specifically for I-greens. And every night we take what we call an zenith sky that we use for calibrate all the spectrum. So basically, we point the telescope at zenith on the vertical, and we stare to the as empty as possible sky to get the spectrum of the sky itself, not of anything that is around there. And then we use that to calibrate the wavelength calibration of every single spectrum. And the other things that, if you're familiar a little bit with near infrared, you know that actually the atmosphere is really opaque in certain specific bands. And so the two bands, one band with like the atmosphere is really, really dark, is actually between exactly the H and the K band. And there is no point observing that region because atmosphere just has sudden time flux. But these extend a little longer through the H and the K band. And so the one that Brian is showing, this little like that looks like blob of light with segmented blob of light is actually atmospheric telluric assumption they're called. That the atmosphere that blocks the entire amount of light that comes in that specific regions. And so in that region,
it's ridiculously high resolution.
It's
I mean,
ridiculous.
it's just, I've never seen anything like that with you see these clear breaks in between.
Because you didn't come to all the against the meetings. No, it's beautiful. Actually, as you can imagine, if you lower the resolution, what actually happens that you collapse together all these blobs. And then instead of having like these sharp lines between one and the other, you have this like more of continuous curve. And it's much harder to correct this continuous curve because this line in the atmosphere keep changing and go one is stronger, one is weaker. And so the cumulative effect for this line is really complex to model. But when you distinguish every single one of these lines, you can model every single of this line in a independent way, basically. And it's much easier to correct for these atmospheric absorptions. Good. This is actually, that's for every, so this correction is so important that for every single observation we have, we take at least one of these, what is called telluric stars. That allows us to correct for both the assertion atmosphere and obtain what is the real flux that is emitted by our real object. And atmosphere at this wavelength changes so much that the rules of the Gemini is that for every 1 hour, 1 and a half of time on sky, we need to have one of these calibration stars observed. So if say that your target is 3 hours long, you need to monitor a target for 3 hours. You need to take at one of these stars at the real beginning that is valid for 1.5 hours. And then at the end, you take another star and then it's valid for the pre-antecedent 1.5 hours. So you need to have 2 of these telluric stars every 3 hours of observation. And so on.
Okay.
I was wondering, since you mentioned the observations, if we could take a look at the way that I-GNIRS 2 is actually observed at our telescope. So I guess there's software that's used to actually set up the observation and everything. Might we take a look at that and just see what I guess Charlie's going to be doing later. Charlie, how are things going in the control room? Are you guys in a holding pattern right now?
So got a couple of things going on right now. One, probably the first and foremost thing is we've closed the dome. We've got some clouds really encroaching on our eastern plateau. So it's really close to us. Brian, I don't know if you can switch over and look at LD1 screen 0, but you can see our quick loop, our cloud cameras there. And just see what that looks like right now, what we're seeing. It's kind of scary. We're watching humidity very closely, but we've closed up the dome in the short term. So if you look at that lower left image, that's looking towards Hilo. You can see moonrise over there. And those clouds are really just below summit level. So and they're moving very quickly. So that could, if that rises just a little bit more, it could come and roll right over us. So we've closed up for the moment. So that's probably first and foremost, because telescope safety is the first thing, and humidity is very bad for our optics primarily, but for everything else. One of the operators' jobs is to ensure the safety of the telescope. So, we're looking at weather for two different things. I'm looking at it from a point of science as the observer. The operator is looking at it from a point of system safety. So we've gone ahead and closed for the time being. We're just going to watch that and see what happens. We're also, the reason I'm out here is that we are currently in the midst of troubleshooting an error with one of our detectors, one of our workhorse detectors, GMOS, which is Gemini Multi-Object Spectrometer, is having a little bit of a fit. So the operator, Layla and Denise, are on the line with one of our instrument specialists who are trying to sort out that problem. So we always have a bunch of people who are on call to help us sort out problems that we can't fix ourselves. And there's a lot that we can do. Sometimes we need to call in the experts, and so they're available. We'll call them any time of night if we need to. So very glad that I could call them at 9:30 at night rather than at 3 in the morning. I always feel bad calling at 2 or 3 in the morning. But they're great. Even in that, they're right on it, and they help us out a lot. So that's kind of where we're at.
All right. Well, thank you for stepping out to give us some insights into what is going on, all the action.
It's a little bit crazy right now. So we had to, obviously you can look in there where we had to shut off the speakers and everything, because there's a lot of conversation that we need to get focused on right at the moment.
Absolutely. And that's always the priority. Well,
yep.
All right. Thank you, Charlie.
Thank you.
Is there any way that we could see the migrants to just basically like the basic GUI? Thank you, Charlie. Okay. Emma, you want to break down what we're seeing here?
Yeah, so that's the way we take data with Agnes 2, or we center our targets with Agnes 2. So that's the image that Chen was showing. Oh, cannot find. This is this slit viewing camera SBC. Oh. And that's basically is the lights. This is the way we can detect sources. So typically we have a star here. I'm getting better in drawing stars. This is a star here, and we say, okay, this is our target. And when we click on this target and say, this is the object we want to observe, and then we click on center down here, and then automatically the software is smart enough to move this lead, that is where the lights we want to enter, to go exactly above the target. And so what's happening that while you're observing, when you're observing, what we have is that your star is actually appearing exactly at the center of the slit, or better, depends on what you're doing. You see that there were two square there. One was blue and one was red. And one is the two position of where you want to put the target. One on the left side of the slit, one on the right side of the slit. We want to do that because when the target is on the left side, then we can use the position when the target is in the right side to actually remove every single signature from the sky. You know, all the vertical lines we were showing before. So that can be removed by simply doing, I take the source in one target in one position, and then the source in another position. The sky will not change in the meanwhile because the sky is everywhere when you're pointing. And so you can subtract one from the other, and you will have, as a resulting feature, you will have one positive emission of the star and one negative emission of the star, but with no no sky present there.
How long is this loop?
Hmm?
How long is this loop?
5
5 arc seconds.
5 arc seconds. Okay.
So
So if you have 2.5 arc seconds seeing,
that's really depends. Or
what happens?
or if you have really good seeing, but your source is extended, that's the same condition. So instead of moving the source between the position we call A and B, we move it outside. So if you have like a big galaxy here, and now you know that there is nothing up here, you call A position the position of the galaxies, and B position the position of the sky. And you take your spectra of the galaxy, then you move to the sky, and then you go back to the galaxy. And so you're always able to subtract emission from the sky in that way. There are few other tricks that are actually nicely implemented. So this region, you can see P and Q, and actually is possibility of moving the telescope or the slit along the slit itself. So in Q direction means you move you can move in this direction along the slit, while in Q direction, and in P direction you move this way. So basically means that while we're observing, we can see, oh, our target is escaping from our slit, and so we want to pop it in a little bit, and so we place minus P a little bit, and we move it back. But we don't trust us that much, and so there is also a way to do this called
you in particular.
I don't trust myself that much, so there is also a way to do that automatically. This is called this slow guide. So basically, the algorithm, when your source is here in the middle or in A and the B position, you expect that when you're perfectly centered, you will have as much light loss from the slit on the right side, on the left side of the slit. So the algorithm will measure the amount of light on the left side and the right side, and will try to make them as equal as possible. So while you're observing for a long time, you will keep the target exactly in the center of the slit. And so that's really a smart way to proceed, because then you're always sure that your target will fall inside the slit. Other nice thing that we have here there's a lot of canceling. Is all on the left side. You see there are a lot of art bit and a lot of things that are popping out, getting green, and of the usual green is good. So these are allowed while we are observing still to monitor the status of the detector, the temperature, that everything goes in the right way. These are two different zooms. These and these are two different zooms that allows us to monitor better where the source is while observing. And this basically, this is what the slit viewing camera is doing, these the right things. And then we have another software that allows us to actually take the data and it collect the data through the slit. But these are, while we are observing, basically what we do, we click on continue, we click on exposure, and this is image keep being taken every 1.63 seconds. That is the shortest amount of time we can collect data. And it keeps telling us we are exactly in the center of the slit. Everything is proceeding well. We feel warm and cozy inside, and we keep going. Everything else? Oh, and we have one other thing. We have the other smart option. You have the off-slit guide that basically say that your target is really tiny in the center of the slit and you don't have enough light on the right, on the left side to say if I'm perfectly centered. And you have another target here that is bright enough that it can be used. So you can select off-slit guide, and the telescope will make sure, the instrument will make sure that this target is always in the right position, and automatically given that the distance between the two sources will not change unless some specific things happen in the sky. We can be sure that the target is always on the center, exactly the center of the slit. I think that's
Sky subtraction. If the target is too faint and sky background is too bright, then we can mark sky and subtract the previous image or the marked sky image. I forgot. Okay. And then we can clearly see the target in the sleeping camera using the subtracting the sky images. That's what we're doing, the target acquisition using the sleeping camera. And once target is on the slit, then we take the science data, the spectrum.
That is actually, it's really nice because it's really intuitive how to proceed with that. So even at 3 in the morning when you're like half asleep and you really don't want to be awake, you can still most likely do the right things at the right time.
Well, I am really excited for you all and looking forward to when iGrins 2 is ready for the community to use so that it can be featured in a Shadow the Scientist session. Charlie mentioned that the clouds have now reached the eastern portion coming up the summit. So what does that mean for observation tonight for iGrins? It will be pushed to later in the evening?
Yeah, I'm not sure. Yeah. Well, so the first observations were planned for around midnight.
Around now.
Okay.
So yeah.
Okay.
So this is system verification. We prepare for all the targets in different weather conditions. So we do have the bad poor weather conditions target, and this is about we can observe that target, but now it's really too bad to open the telescope. So we're waiting until the cloud's gone, and then we can open it and then observe some of our SV targets tonight.
So this is the sixth night, the SV run?
We have 7 nights and this is 6th night. Yes.
6th night. Okay, so you guys have presumably got a decent amount of data at this point.
Yeah.
Anyways, I mean, it's always helpful to get more data to test more science cases, but if things don't work out tonight, well, you have tomorrow night, but you also have a lot of other data, so you'll be able to analyze the system, whether it's working correctly in the way that we're happy with at Gemini. Or
unfortunately, the first and second night was great. So we have all the great science data. So we're happy about it. But we still want some.
Yeah, unfortunately, my target has not been observed yet. So
it's not really that interesting.
I know it's
black holes at the beginning of time. It's
it's not. It's kind of boring. I agree with that.
We still have hope. Wait.
But so I mean, in all seriousness, I mean, if the humidity's risen, likely it's going to be another. Even if things clear, it'll be another hour or more before any observation would be taken. So it doesn't mean that we're done for tonight. It's 10:00 p.m. here in Hawaii, so we still have a long night to go. And we'll see what happens. Things change very rapidly on Maunakea. You never know what's going to happen, so we usually stay here until the bitter end. Tonight that'll be Charlie, Layla, and Denise keeping watch and keeping guard and being ready.
Well, thank you so much, Heywan and Emma, and the rest of the CASI team for being with us in this session to give us an in-depth understanding of iGrins 2. We certainly look forward to having you all again with us when iGrins 2 is ready for full use. So back to the rest of the team in the other room, Brian, Emma, Heywan, and Emily. Emily, would you like to talk about some outreach activities coming up for Gemini?
Yes, we got a really nice big event. I'm gonna let Brian drive the screen. Gemini Observatory, we are open for public visits and tours, both of our base facility and of our telescope facility. You can sign up for those via our website. Very easy, pretty easy to sign up, a little bit hard to find, but very easy to sign up for. Also, if you are on island in August, we have a big event that we are planning with the rest of the Maunakea observatories here on North Oahuku Place, which is sometimes called Observatory Row. We're going to have a block party celebrating both the Tanabata Festival and Legend, as well as, oh, we never mentioned this. This is the 25th anniversary of First Light here at Gemini Observatory, and both for Subaru telescope. So we're having a big block party where it's going to be food trucks, there's going to be science presentations, a bunch of organizations coming together completely free, and we hope to see you all there. And we do many other opportunities in addition to all of our programming. So keep track of us on the social media channels. And of course, we hope to see you at more Shadow the Scientist sessions. I know I was just looking at the Shadow the Scientist website, so I'm not sure if Jamika wants to plug any of the upcoming amazing Shadow the Scientists that are coming up as well.
Thanks, Emily. I would definitely like to. But before that, I will say I put a link to the public visits to Gemini North site where you can sign up. And I know when people start to sign up, it can fill up really quickly, but these sessions, these public visits are done regularly. How often are they done, Emily?
So the visits to the telescope facility is done every other Thursday, and that's the one that really fills up really fast. Going up to the telescope facility, it is driving up Mauna Kea, so you do need to provide your own four-wheel drive capability vehicle for traveling up to the summit. We also do tours of our base facility, and that tour has a lot less restrictions because we're not going up to high altitude and not having to restrict for age. You don't need to be providing four-wheel drive capability vehicle. And the base facility tours happen the second Friday of the month starting at 5 p.m. And that facility tour takes you through our base facility. You can see the control room where Charlie guys are currently exploring right now and see a bunch of the amazing features here at the base facility. And we conclude the night with doing a little bit of moon gazing.
That sounds amazing. Thank you so much, Emily, for sharing that with us. And for those of you who have not checked out our website, share my screen, please do. We're always updating our upcoming sessions, and here are several coming up. One.
Oh, nice.
I might have to do the Hawaii volcanoes one.
Yeah, I'm super excited about it. So first, as they were talking earlier about Mount Wilson, and so we have a session featuring optical interferometry at the Chara Array. The session is going to be led by Nick Scott, who also has been on previous Gemini sessions talking about speckle imaging. And so definitely join us for that if you can. And then, yes, on August 8th, we'll have, so that's our first session with the Chara Array. And then we'll be having our first session with the team at the Hawaiian Volcano Observatory. We'll be shadowing some petrologists as they process some volcanic samples from the June 2024 Kilauea eruption. So you don't want to miss it. It's going to be hot. And before I wrap up, I'd like to say that we have had an observer here with us. Viraja Tatu is from the Canada-France-Hawaii telescope, and Viraja will be hosting Shadow the Scientist sessions later in the year, and she is observing here the Gemini team to learn from some of the best. And I have to say, you can never go wrong observing STS sessions with this amazing crew, because they really show you how well it's done. So, you know, any questions you have, Viraja, you know, we're always happy to help. If you'd like to jump on and give a quick intro so that our audience knows who you are for when they see future sessions hosted by you, please feel free to do so.
Thank you so much, Jamika. Hi, everyone. This is Viraja Khatu. I'm a resident astronomer at the Canada-France Hawaii Telescope. We have our base facility in Waimea, which is up to the north on the Big Island. And yes, I was really happy to see how the session unfolded today. It was really nice to join all of you. I think it was really great 2 hours of observing everything happening in the control room and outside. So yeah, I'm really excited to be a part of this program. I will be shadowing a few more events and before I design my own program. So really happy, and thank you so much for allowing me to join here today.
Absolutely, Viraja. We look forward to that. I'd like to thank all of you for being here with us. Denise, Layla, Charlie, I know you're working hard there in the control room. You've been amazing. Thank you for letting us shadow you. And I will send it back over to Brian for our last word.
So I just want to thank everybody for joining us, and it's wonderful to see more members of the Maunakea Ohana coming and offering sessions for Shadow the Scientist. I think with CFH joining, that will mean that we'll now have had Shadow the Scientist session on every large optical near infrared telescope on Maunakea. We'll have some additional sessions with my research group on Subaru coming up later this year in October and November. So it's really nice to see, well, Jamika, you've done wonderful work to expand Shadow the Scientists beyond astronomy, but within the astronomical community, just seeing more interest, more people interested in sharing all the wonderful knowledge and all the wonderful capabilities that we have here in Hawaii and around the world. And Cassie team, thank you so much for spending the time and talking to us about, well, I learned a lot. I didn't know a whole lot about IGRINS2 before tonight, and it was helpful to hear from you guys and all the passion that you bring to the instrument building, and you guys as well. So yeah, thank you everybody and all the participants that came on, and look forward. We're going to have another session sometime next month. So please look for that for Gemini North, and I may be going down to Gemini South at some point in the not so distant future. So we'll try for a session down there as well. So thank you everybody.
Thank you. And Emma, if you get in.
Thank you so much.
I just noticed you guys are both wearing diffraction gratings.
Yes.
H-band,
K-band.
Okay, good night everybody. Thank you.
Bye.